Okay, so for the quiz, state the definition of pairwise joint index family of sets. What Clyde was saying, an index family A of sets equals, yeah, you can write that. The whole, yeah. It's just joint, if and only if. Mm-hmm. The intersection is empty, they're equal, yeah. Question?
How about if I put A out by four, do they have and?
No, not and, it's or. It's important, that's an important word. You don't have to have that, that's included in the two properties of it. Then that'll be partially off, yeah. Okay, how about the last theorem on there? Let A be the set A alpha, alpha triangle. B and what? Yeah, our second quiz question. I'll put it up here. Let's see, 2.3. So, looking at the second one right here. So what is that first line right there? Index family. Then, okay, we got to make this bigger. Do what? Say that again? Yeah. Yeah. Then the intersection A sub alpha, what goes here? Yeah, it is a subset.
Because we put a line.
A sub beta. Sorry, I didn't mean to do that. For each beta and triangle. And then A beta is a subset of the union of alpha and triangle of A sub alpha for each beta and triangle. And then this is De Morgan's laws. The complement of the intersection is equal to the union of the complements. And then the complement of the union is equal to the intersection of the complements. So I got. Okay, so that was our quiz. So what are we talking about today? 3? Oh, before I get going on section 2.3, I need to tell you guys that for the outline for section 2.4, you're not going to do all of section 2.4. Yeah, you're going to want to mark this in your books. Yay. We're going to outline. And the examples here, if they say proof, I need to have the proofs, just anything that says proof on it, we need to do the way we've been doing proofs, even if they go with examples instead of theorems. So you are going to actually outline through the end of the proof on page 105 at the top. So before the example starts on page 105 about lines and stuff like that, we're not doing that or anything else to the rest of it.
So just go up to 105.
To the top of 105, to the end of the proof at the top of page 105. Yeah, the beginning up until the top of page 105. Yeah. That's it that you're doing for the outline on that one. So it'll be a shorter outline. Or change. Okay, so, yeah. But there's more proofs in those 2 pages, hence the shortening of it. The book uses script letters to denote families of sets. You're going to use italics. when you're typing it up. I can use calligraphy because I have workplace, but they don't give you calligraphy in Scientific Notebook. They just give you. I'm gonna try. There we go. Yeah, definition, it says, let A be a family of sets. The union is all X and A for A. So it's everything combined together. You're combining everything together here for the union. What would the intersection be? It's one that's in everything. It's all the elements that are in all of the sets. Okay. And then after that definition, we're just running through all the definitions real quick. We have an indexed family. What was this indexing family used for? Yeah, that's a very good question. That's usually the question you guys are asking me. It's simply the list of names of your sets. So if you want to think about this as something we use all the time, it's the address of the set. So think about when someone sends you email. They're sending you a message, they send it to your address. Okay? So it's the name of the set. Or if you want an apartment complex, it's, if you live in apartment 2 on the 3rd floor, then you would have 302 for your apartment number. So it's the number of the apartment that all the elements live in. It is simply the naming convention. That's all it is. It has nothing to do with what's inside the set. It has everything to do with what you're calling the set. And that's all it's used for. Don't let it confuse you. It really isn't confusing. Yeah. Yeah, the building would be the family. Yep. Or you'd have a subset would be a floor. Yeah, that's exactly correct. And then pairwise disjoint, that was on the quiz. Either the two sets are equal or they have nothing in common in the intersection. The book gave some examples of a family of sets that were not pairwise disjoint. What happened to break pairwise disjoint? They had a non-empty intersection, but they weren't equal to each other. So if you had, suppose you have 1 and 2, and you have another set that's 2 and 3, and our big set. Is that set pairwise disjoint sets? No, because we have 2 that's common to both of them. And as soon as you have an element common to 2 different sets and the sets aren't equal, then they're not pairwise disjoint. We need pairwise disjoint for theorems that we're going to end up proving later on in this book. Okay, so to some of the examples. Notice that I didn't choose the brackets that put it underneath. You can use either one in the notation. If you want to use the intersection and just do Control L, it'll put it down here beside it, just like a subscript. That's equally acceptable in mathematics. So you can put it to the side. Usually when it's on display, it's because I have it in a table, it's putting it on the side as well. So let's look at the set A sub n, n equal, n in the n plus 1 and 2n is in A sub n. So I want to know, let's look at A1 just so we can get an idea. What would be in our set A1? Yeah, 1, 2, and 2, which would be 1 and 2. How about in A sub 2? 2, 3, and 4. A sub 3. 3, 4, and 6. A sub 4. A sub 5. And A sub 6. So, how would I answer what is the intersection of A sub I for I equals 1 to infinity? Is 2 in A sub 3? No. So it can't contain 2. Can it contain 1? Is 1 in A sub 6? No. In fact, is anything from A sub 2 in A sub 6? No. So what do they have in common? Nothing. So the intersection is the empty set. How about the union? And this one is I equals 4 to 6. So we're looking at this right here. What would be that union? Yep. Four, 5, 6, 7, 8, 10, 12. I'm going to draw a little line so we can see. Got a little crowded. What would be the union from I equals 1 to infinity then when you put them all? What do we call it when we put it all? How about the naturals? Yeah, and we know it's going to be the naturals just by looking at that right there. That n in the naturals tells us that every value from the naturals has to be present. No, the naturals, the way it is the set of all the natural numbers. Yeah. Yeah, you don't put it in a set. That's correct. Now, let's look at this last one. What's the intersection from I equals 2 to 4? Yep. Just 4. From 2, 3, and 4, those ones right there. Okay, do you guys see how to use a set indexing and stuff like that? It's just the name of the set so you can identify which one they're talking about. And then you do your intersections and unions just like we've been doing. Notice the difference here. This for number 1 is the same thing as this intersection right there. I can write them both the same way. The intersection n in the naturals of A sub n is the same thing as the intersection n equals 1 to infinity A sub n. It's just a different way of writing the notation. And I could do the same thing. Those of you who've in calculus or taken calculus, when we talk about this series, I could naturals of 1 over n. That's the same thing as saying n equals 1 to infinity 1 over n. And you can use either notation. Okay, do you guys all see that? It just means the same thing. Now, let's answer this last question. How would you show that 27 is in the union and in the naturals of A sub n? I scrolled down too far. No, I went up too far. What's our definition for A sub n?
You just have to find the number that.
Yeah. What set do I know it lives in? What value of n? At A sub 27. Yeah, because that one, would it also be in A26?
Yes.
Yep. Yeah, there is, but that one's harder. Okay, that answers all the questions on that page. You have a bunch of homework like that. Can you do that? Yeah, we like that. That's the easy homework. Okay, now they're going to tell us what our indexes are on our sets, what the names of our sets are. And we're going to say AX is 2x plus 4, 8, and 12 minus 2x for x in triangle. So they want us to find out what is A0, because that's the first thing in our triangle. So can we figure out what A0 would be? 4, 8, and 12. What is A1?
6, 8,
6, 8,
10.
10. Okay. How about A2? But we don't have to write it down twice, right? It's just 8. How about A3? 10. Now, didn't we already see those? Yeah, that one's equal to A1. Those are the same. How about, is that equal to A2?
No,
No, sorry.
A2 inside.
Yeah, it's a subset of. What is A4? Yeah. So that's going to be A4. So some of them are duplicated. Notice that there is no A5. Why is there no A5? Five isn't in my list of possibilities. 5 isn't an allowed. You can only use the names that they give you, and 5 wasn't given. Only 0, 1, 2, 3, and 4 are given. So here's a question. How many elements are there in the indexing set? Distinct, but there are 5 elements. How many different sets are there? Yeah. How many sets are there? There are 3 sets. 3 distinct sets. So 5 elements. That means you can have multiple names for your set. No one said that the name of the set had to be unique. Okay, now we have this set. It has B1, B2, B3, B4, B5, B6, and they're all listed here. Is the family B pairwise disjoint? So look at B1 and B2. Do they have any intersections? No. Which two have intersections? B2 and B3, right? But they're equal. B2 equals B3. How about B4? Is that the same as anything? No. How about B1, B5, and B6? Yeah. Are they pairwise disjoint? Yes. Can you do that on your homework? You like that? That's easy too. Okay, suppose that a sub x equals minus x to x for every x in R, and D is going to be the family of a sub x, so the x is in the reals. Find A3 and A minus 3. So what is A3? Yeah, 3 and -3, -3 and 3, whichever way you want to look at it. What's A minus 3? So that's equal to A3. So tell me about these sets D. Does it appear that those are going to be pairwise disjoint? Yeah. That is pairwise disjoint. Okay, now we're going to start on our theorems. For every set B in a family A of sets, the intersection is contained in B. that's an extension of the one of the theorems we had last time. The intersection of two sets is a subset of either of the original sets. And then B is contained in the union of all the A's in A. And then if the family is non-empty, then the intersection is contained in the union. So we're looking at part B only. How do you show set containment? How do you show that one set is a subset of another set? Yeah. For all X in B, X has to be in the union A. So that's going to be our goal. Let's go ahead and just go straight to typing this one because it's not hard to type up. There we go. So what's the hypothesis? Let B be an element in a family of sets A, right? We need that guy. What?
Where is that free?
Gray box.
You agree?
That gives you a page break. Sorry, I forgot to take it out. Let B be in a family of sets. And then we're proving part B. So what do we assume? Yeah. X has to be in the inside set, and then we have to show it lives over here. So if X is in B, what do we know? We know B is one of these sets in our family of sets A. Since B is an element of A, what do I know? X has to be in the union of all the. Now, since B was arbitrary, well, since X element of B was arbitrary, that's what I should say. You don't want control Y. What can I conclude? My conclusion, right? A little two-line proof. Not long at all. Now, let's theorem 11. We're looking at index collection of sets, and we want to do a two-part proof for C. They did it using if and only if. So if I do the two-part proof, I'm going to assume the first side and get to the second and show subsets. So that would be show the intersection alpha in triangle A sub alpha complement the subset of the union alpha in triangle A sub alpha complement. And then go the other direction. That would be the two-part. So how would we show the first direction? You assume x is in the first part? Can I go to typing this, or do you want me to write it first? You want to write first? Okay. If I do the first part, I'm going to let x be in the intersection, alpha and triangle, of a sub alpha, complement. But what that on which one? On this second one? Yeah, it's missing right here. Yeah. So the first part, if you let x be in the intersection, the complement of the intersections, where does that tell you x lives? X is not in the intersection, right? Just apply the definition of complements. But then, where does that tell you x has to live? If x is not in, that means it can't be, it's not in every set. The intersection says it's in every set. So x is not in every set a sub alpha, alpha and triangle. It has to be outside one of them. Many times we skip step 3 right here and go straight to step 4. If you know it's not in the intersection, you know it has to not be in one of the sets. But if it's not in one of the sets, then step 5 says a beta complement. But if it's an a beta complement, then step 6 says it has to be in the union of a complement. Particular set, it's in the union of all of them. And that's going the first direction on it. Going back the other direction is just the same. So, where it is. Let's go type it. So let's get our hypothesis. Let that be an indexed collection of sets. And to go the first direction, we're going to let x be in that complement right there. Then, if you could see the written part, then apply the definition of complement. On this one, it's much easier. By the definition of complements, I know that x has to yeah. This is easier to write it this way. X is not an I can write it this way. X is not an element of the intersection. Take the complement and the parentheses off. By the definition of intersection, I know that x has to is not in a sum beta or some beta in delta. And then that tells you that's supposed to be a negated one right there. Let's get that negated. If it's not an A beta, apply the definition of complements. And then you know that X is an A beta complement. It's supposed to be X. What does that tell you? I could just copy. Yeah. Since X was arbitrary, was that, and this is set containment. Now, how would you prove it going back the other direction? Could you do that on your own? I'm running out of time, that's fine. I'll let you try it. I would be able to do that because this question has ended up on the test before. Just one of the directions on it. So make sure that you can do. The last thing we're going to do, and then we're going to do the homework problem dealing with the disjoint sets because that's a hard one. We want to be able to prove, let A and B be two pairwise disjoint families of sets. Let C be the intersection of A and B. Prove that C is a pairwise disjoint, a family of pairwise disjoint sets. There's the hypothesis. What do we have to do to prove pairwise disjoint? Yeah, for any two sets in there, I have to show that either they're equal or the intersection is empty, right? Okay, so when we're trying to prove that, what we do is we say, we need two sets in there. So I'll do A and B, the element of our set C. Well, no, it's going to be different than that. I need to show that either A equals to B or A intersect B is an empty set. Yeah. So what I'm going to do, I'm going to show an or, not one, and show the other. You have to do it for both of them. So for the first part, I'm going to assume, well, actually, I'll just say first. Assume that A is not equal to B. What do I know about A and B? I know A and B live in our set C, right? And what is set C defined to be? A intersected with B, our capital. Do you guys not like these being A and B? We could call them B and Q. So that okay. So assume that P is not equal to Q. Since P and Q are in C, and I know C is equal to A intersected with B right here. These are my script sets. I know that P and Q have to be in our script set of A. Yeah. A and B are pairwise disjoint. So if I know P is not equal to Q, then by definition of pairwise disjoint, I have to know that P equals to Q. A is pairwise disjoint. I know that I was jumped ahead to the intersected with Q is equal to the empty set. That's our definition. That's the first way. Let's look at the second way. P intersected with Q is equal to the empty set. Sorry, is not equal to the empty set. We negate this one. So you negate one of them and show that it has to be the other one. So I'm assuming P intersected with Q is not equal to the empty set. What does that tell me? Yeah. I need all of this right here, and then we'll just make that one change. So I know that either P equals to Q, or P intersected with Q is equal to empty set. Thus, since P and Q are arbitrary, it follows that C is pairwise disjoint. Pairwise disjoint is an either or argument. So you have to assume not equal, show intersection is empty. You have to assume the intersection is not empty and show equal. Okay, you guys have a pairwise disjoint on one of your homeworks. Let me put up your homework so you guys can see what it is. And that's the one you're going to work on in class. Okay, number 13 is the last one on the homework. That's a hard one. That's the one that you guys are going to try and prove right now. And then when you get done with number 13, you can just work back on the other ones until class ends in another 11 minutes. I should stop the recorder.